Right. Hello, everybody. I'm very glad to be here with you today and to give a little bit of an imposter talk. So I'm mostly active in the Elm community, but I am a lurker in the Gleam Discord, mainly thanks to Haley, who is like a bridge between those two communities. And so I always had this envy in me for the Beam, and I've played with Erlang, played with Elixir, played with Gleam, and I always kind of envied that you can just like spawn processes, and they have this like selective receive and all this stuff, right? And uh, I wanted to understand how it kind of fits together, how it works under the hood, and what better way than to try to write it yourself in possibly a bad way, but that's how we are going to learn the most. So a little bit of expectation management. I am not going to be summarizing the Beam book. I honestly don't even have it yet. I want to buy it. I want to read it. But so this talk is not about whatever the real Beam is doing. This is more about writing a toy implementation and trying to understand the concepts. So I want to focus only on the main ideas, or what I think are the main ideas. And I'm going to be skipping a lot of things that you would normally do in a real virtual machine, in a real compiler, in a real interpreter. So I will just be doing the minimal stuff to kind of help you see how it ticks, but it's not going to be what's best in production. And so this is what I'm going to be focused on. So spawning processes, sending messages, receiving messages selectively, links, supervisors, stuff like that. So with that out of the way, let me show you what we are building towards. You can see we have a few instructions, and this might be different from what you're used to. So normally, in a normal compiler or interpreter, you would have a list of statements that kind of live in a list underneath each other, but that would force me to, hold environments, think about scopes, bindings, stuff like that. So instead, I want to do things with continuations. So, there are these terminal nodes that kind of, end and crash. You just like stop the program, but all the other ones have a continuation. And this is just a function that will give you the rest of the program. So this is how such a program might look like. Again, I'm not going to be writing a parser, lexer, anything like that. We will just have these hard-coded examples. And if you are confused by, so this is written in the Elm language, if you are confused about the arrows, this is just a way to have fewer parentheses, right? So, okay. We've got to start somewhere at the terminals. So for the end program, there's not much to do, but it will allow us to talk about the basics of the implementation. So we want to really implement a scheduler. And right now, it doesn't have to hold anything other than the program. And since the program is possibly just the end instruction, we just do nothing in the step function that will be, I think, the main meat of what we are building. And I can use this opportunity to show you a visualizer. I think this might be big enough. So right now, we only have the end program, and I can only make one step, right? And if I step, it says it ended successfully. Cool. So let's do something else, and let's do a little bit of hand waving, and we're going to say there's a bunch of work that these processes need to do, right? This might be some calculations, there might be some function calls, we don't really know. I'm not going to care. I'm just going to say this program does 5 units of work, whatever that is. And So now we have a new instruction to implement, and for now we don't really have to kind of do anything about it. We can just ignore the integer. We can ignore how much work it is. We're just going to say it's done, and we can now use the continuation to get the new program, the rest of the program. Let's see that in action again. So now we have a program with 5 units of work, and then it's going to end, right? And so I can step twice, and it does the work and ends. Now, let's do something more interesting. This is getting into why I am doing this. So how does spawning processes work? So we have a new instruction, spawn a program and then continue with its PID. So you can see the continuations are getting some argument if they need to. And so here the example program will work a bit, it will spawn a child, it will work a bit then as well. But in the meantime, the child can run, right? These are concurrent. It's all single-threaded, but it can be concurrent. They can like interleave. And the child just does a bunch of work and then ends. So suddenly we can have multiple programs. We can have multiple processes. So instead of a single program, we are going to hold them in a dictionary, in like associative array or a map, because we will need to kind of get them by the PID. And there's a new concept that's called the ready queue. So it's a queue of PIDs for processes that are ready to be run, right? They are not running all the time. They are waiting to be processed. And so the spawn function that I have used in the init function, it basically does this little bit of boilerplate where it finds out what PID is not used, and it uses it for the new program. It inserts it into the list of programs, it increments it, and then enqueues the program, right? So that it can actually run. And enqueuing means just put it into the queue, put it into the data structure. And here we have a little bit of optimization where we only put it in there if it's not already in there. And now the step function needs to change because we don't have one program in the schedule anymore. We have a whole dictionary of them, but we need to know which program to pick, and we use the ready queue for that. So we pick the first item in the queue and try to use that PID to get the whole program. And if all that succeeds, we can now finally do what we did before. And so what we did before, again, needs to change a little bit because we can't, again, there's multiple programs, not just one. So you can imagine this set program function just like reaches into the dictionary and sets that program in there. And enqueues it again because we have used the continuation. There's a new program that we haven't run yet. So we definitely want to try and run it. Now, this new instruction, spawn, reuses the helper that we have already defined and used before, right? Spawn. We get PID from it, which we can use for the continuation. And so we let the parent remember its new program. We enqueue the parent. And the child is already enqueued because the spawn function does that. Let's see that. So we have the example from before. So let's try to run through it. You can see, we can see the ready queue, and we will see like a table of all processes. So the parent runs, spawns a child, and now the child is at the top of the queue. And so now the child will run. So the child does 10 units of work. Now the parent runs. So you can see they kind of trade places and kind of share the CPU. And everything kind of goes well. Can you see what problem could be? What problem could happen? What if the child does like really a ton of work, right? What if it like hogs the CPU for 10 minutes? So right now, what we have is kind of a cooperative concurrency where you expect the other processes to behave well, but they don't have to, right? So PID1, the child just runs a lot of work before the parent can run again. So this is not ideal. And a way to combat this is with a reduction budget. So some of the talks in here have already talked about this. You pick a number. I have picked 7 because my examples are small, but the real beam has like 4,000. And the real beam basically decrements this reduction budget whenever a function call happens, which works really well for beam languages because we recurse when we like process lists and so on. So it ends up working really well. For me, I do not have function calls in here, so I'm just gonna use the integer in the work instruction to kind of hold that amount of work. So we pass that reduction budget from the top to the step inner function, and now we have a bit of new logic. So if we don't have any budget left, if we don't have any budget to spend, then remember whatever program you ended up with, and if the program is something interesting, I really should have like a program here. If the program is something interesting, then enqueue it again, meaning for the end instruction, we don't really need to enqueue that because there's no more work to be done. If we do have budget to spend, so this is, budget is greater than 0, I do have a few helpers. So this one basically says, whatever budget you had, now you have 0, please end, stop everything, and continue lets you set the new budget, right? So we can use those right away. So for end, whatever budget we had, we just stop, set the budget to 0, and in spawn, I kind of arbitrarily do this. The real beam might not be doing this, I don't know. We decrement the budget by 1 whenever we spawn. Now, what really changes, all right, so there's a few more slides. What we really want to do is get from this situation to this one, right? So right now, the child does everything while the parent waits, and we want them to kind of trade places so that both can run in like regular intervals. So most of the work happens here, where in the work instruction, if there's no work to be done, we just use the continuation. If there is work to be done, we figure out how much work can we actually do, right? So there might be like the 999 units of work, but we can only do 7. So this like min calculation will do that. We propagate that, so we remember the rest of the work, rest of the budget, and we recurse. And so we can now see if that problem is really fixed. So as you can see, we've got the bad child in here. This is the old kind of algorithm. So this is the problem we wanted to fix. And if I go with reductions budget, we can see after the first step, the parent did a bunch of work, right? So it did the first amount of work, it spawned the child, and then it did like 2 out of the 5, and it has 3 left. So that kind of makes sense. Now the child runs, and instead of the whole kind of huge work, it only does 8 reductions because that's what I have here. And now the parent can run again, PID 0. So the parent does the rest, the 3 leftover units of work and ends. So we can see that here. And now the child is the only thing running and can finish. So that's good. So that's how we get to an illusion of preemptive scheduling using the reductions budget. You could still have kind of bad programs that have a lot of computations in them that will just like not yield and not trigger the reductions budget, forcing them to yield. So you still can have bad behaved programs, but it's much harder, or like it's not as often that this happens. Let's go for something else. Let's send messages to other processes. So again, we have new instruction, send a string to a PID and continue. And so here's an example. We're just going to send ping to it, but the child doesn't have any way to receive that message, so it's just going to ignore it for now. So now we have to extend our process. Suddenly it's not just the program, it's also a mailbox, right? It contains a mailbox with the messages that others have sent to it. And we have new instruction. I have hidden most of the work behind a helper, so let's see what the helper does. And the helper just reaches, because we have access to the whole scheduler, so we can do that. We can like reach across processes. We reach into the destination and save the message into the queue. And that's really all there is to it. So let's see it. You can see in the visualizer we now have a mailbox. So the parent will spawn a child, cool. It wants to send a message to it, but now the child really runs. Child just does some work, and now the parent can send it a message. And after we do that, we can see that the child has a message in its mailbox, but doesn't really care. Okay, so to kind of fix that, let's receive that message. And I am simplifying here a lot because in Erlang and other Beam languages, you can do a lot of things in those selective receives, right? You have multiple branches, you have multiple patterns, you have pattern matching, which I'm not doing here at all. You have timeouts, you have default branches. And so what I am implementing here is just waiting for a hard-coded string message, right? And unless I receive that message, I will not continue with anything. I will just sleep and wait for the right message. So yeah, here's a little bit of optimization. Let's say I have went through all of the messages in my mailbox as I'm trying to receive, and none of these messages match. So I don't really need to run again and try to go through the list again until I have a new message. So I don't want to re-enqueue this process if there's no interesting message in the mailbox. So that's what this does. And now the implementation of the receive function is kind of huge. That's like the most code I will be showing. So let's instead talk about it in pseudocode. When you are receiving a message selectively, you kind of go through your mailbox and see if any of those messages match. If one of them matches, you remove it from the mailbox and you user continuation and like go on with the rest of the program. If none of them match, you leave the mailbox as it was, so all messages are still in there, and you go to sleep, right? You don't enqueue again. So that's what this does. You will have to believe me, I don't have too much time to like talk about it. It is what it does. Let's see if this works. So we are going to spawn a child. The child is going to wait on a message immediately, but it has nothing in its mailbox, so it's going to wait. So it's now sleeping. It's not in the queue, right? We are going to send the ping message to it, and this wakes it up. So now PID1 is in the ready queue. It has the message in its mailbox. It's waiting for that exact message. Everything lines up, and it will next try to do work when it next runs. The parent is done, and the child can finish. So that's sending and receiving messages. One last piece of functionality that I want to implement, because this is really kind of what gives you all those like supervisor trees and so on, is the ability to link between processes, which just means if a process exits, we are going to send a system message to other interested processes, right? That wanted to know about this, that are linked to it. There are also monitors, which are one-directional, but I'm going to do the bidirectional links. And so here you have how we will do this. So when you link to a PID, that process will now hold your PID in its links set. That should be straightforward enough. There's not much to say about this function because link is something you want to do. Crash is like there's no more work to be done. So let's. Sorry? All right. Yeah. I will be ending soon. So when you link, we are gonna say for both of the PIDs, right? It's bidirectional. We are gonna add the link to the set of links. When you crash, that's when we are gonna actually use that set. So we are gonna go through all of the links and for each of them send a system message to that PID. And for my last demo, let's see it. So I'm gonna spawn a child. It's gonna crash immediately. I want to link to it, but there's no more child to link to, so I crash too. This wasn't supposed to happen. Do you see the bug? It's not atomic, right? So something got in between the spawn and the link, and the child managed to crash in the meantime. So let's make those an atomic instruction. We spawn link. This is guaranteed to succeed. The child crashes. We get a message from the system. We receive on the message and gracefully, right? We weren't, it like didn't drive us down with it. We can kind of react to it in whatever way we want. So that's it. That's all the functionality, and it's few interesting primitives that like many virtual machines or languages don't have, and they built in this nice way to give you that like functionality that and like reliability that Beam provides, supervisor trees, and so on. So I think that's genius, and I hope you like this. This was Build Your Own Beam.
Thank you, Martin.